Hello and welcome. So here I'll explain how to take the Laplace transforms of the first and second derivatives. So really quickly before we get into it, I just wanted to go over some notation. So this right here means the Laplace transform of f of t, and so we can rewrite that transform as capital F of s, just means the Laplace transform of f of t. And the actual definition for how we solve for that capital F of s is this integral right here. And so we're going to use this integral, this definition, to solve for the Laplace transform of the first derivative right here, and then later the second derivative. Okay, so this is going to be the integral from 0 to infinity, just from the definition up above, of f prime of t e to the negative st dt. And that f prime of t is because we're taking the Laplace transform of f prime of t, and whatever we're taking the transform of appears right here in the integral. Okay. So this is going to be an integration by parts, right? Because we see a function of t being multiplied by a function of t. So here we're going to say u equals e to the negative st, therefore du equals negative s e to the negative st dt, right? And so then what does dv equal? Well, just the other term in our integral. That's going to be f prime of t dt. We take the integral of that guy to get v, and we just are left with a f of t. And so maybe it's obvious why we chose u and v after sort of going through that derivative and integral. It's because we wanted to reduce the order of the derivative, because the integration by parts formula is uv minus the integral of v du, and we wanted that integral to be easier. And so with u being e to the negative st and dv being f prime of t dt, we're going to take the integral of f of t instead of a second derivative if we had chosen u to be f prime of t. Okay, but let's just go ahead and actually evaluate this now. So this is the same thing as uv, right? So e to the negative st times f of t, like so. And then this is going to be evaluated from 0 to infinity. And we get to subtract the integral from 0 to infinity of v du, right? Just following the integration by parts formula. So what's v du? Well, we kind of have it written right there. F of t times negative, but that negative is going to cancel with this pre-existing negative. We'll just have an se to the negative st dt, like so. Okay, so what is this right here? Well, what's e to the negative st times f of t at infinity? Well, it's being multiplied by a e to the negative infinity, and e to the negative infinity is always 0. So we're going to be left with a negative e to the negative 0 times f of 0. What's e to the 0? It's just 1. So actually this is a negative f of 0 right here. Okay, so now we need to evaluate this guy. And actually we have everything that we need to evaluate this integral. If you remember the definition up above for what the actual Laplace transform is the integral of 0 to infinity of f of t e to the negative st dt. And we have that exactly right here, right? The f of t, the e to the negative st dt. The only thing that's different is we have an s, but we're taking an integral with respect to t. So actually we can kind of just take that s outside of the integral. And so then we're going to be left with plus s times the integral, which we defined as f of s, right? So this whole piece of our problem right here is s times f of s, like so. And so what does that mean our first derivative is? Well, we can finally write out our first derivative answer right here. That's just simply going to be negative f of 0 plus s f of s, like so. And so you can see by just using the definition of the Laplace transform, we found this pretty nice and easily, right? And so let's just go ahead and do the exact same thing for the second derivative. Okay, here we are, and so we're going to start this one just like we did with the first derivative. This, just by definition, is the integral from 0 to infinity of f double prime of t e to the negative st dt, like so. Okay, and again, we have a function of time being multiplied by a function of time, so we're going to have to use integration by parts. And so we're going to use the same integration by parts here, u equals e to the negative st, which means that du equals negative se to the negative st dt, like so. dv is then going to be, let's see, f double prime of t dt, And then v is just going to be then the first derivative of t, right? Okay, and so that's pretty nice because we're trying to reduce the order of the derivative, so inevitably we know what that integral will be, right? And so with this choice of u and v, we were able to reduce the derivative of f. Okay. So this is just by the integration by parts formula, uv minus the integral of v du. So what's uv? Well, we have a f prime of t, and then we have a e to the negative st. Now we want to subtract the integral of v du, right? So I see du has a negative, and I have a negative here as well, so this is going to turn into a plus. And then I see du has an s, which we can take out of the integral. So this is the integral from 0 to infinity of v du without the negative s right here, right? So that's just going to be a f prime of t times e to the negative st dt, like so. Okay, and this right here, this guy is also going to be evaluated from 0 to infinity. Okay, but we kind of just found what this integral was up above, but we can sort of use the same techniques to find it again in terms of the second derivative. So this is f prime of t, e to the negative st, 0 to infinity, and now we want to evaluate this integral, right? And so again, we're going to use integration by parts. So here, let's say that u is going to equal e to the negative st, as we have done before. Du then equals negative s e to the negative st dt, and then so then we're left with a dv of f prime of t dt. Make sure you can see everything on the screen. And then we're left with v equals, well, what's the integral of a derivative? It's just the original function. Okay, so plugging this new integration by parts into this bracket right here, we have uv, so e to the negative st, times v, right, which is f of t. And then we have minus the integral of v du. So what's the integral of v du? And this is still 0 to infinity. Well, v is f of t. Du is a negative s, so we can turn this into a positive sign and then bring out an s. E to the negative st dt, like so. Okay, and then this guy right here is also evaluated from 0 to infinity. Okay, so what we can kind of do here is just evaluate everything that needs to be evaluated, right? So this guy right here, let's start with this. What's the, I guess, infinity minus 0, right? What's that evaluated? So f prime of infinity, e to the negative infinity is going to be a 0. Then we have a minus because we're evaluating from infinity to 0. And so what's this? It's going to be f prime of 0, e to the negative 0, but e to the 0 is just 1. So here we have our first piece. What about this piece right here? So we have a s, so we can kind of take that out of what's about to be evaluated. As we know, it'll be distributed to everything in this order of brackets. Okay, so e to the negative st, f of t, evaluated from infinity to 0. So again, we're going to have a 0 minus because e to the negative infinity is 0. So what's e to the 0 multiplied by f of 0? Well, that's just 1 times f of 0, or in other words, just f of 0, right? Okay, so now we can kind of add, and then we have a s coming from outside of this large bracket, and then another s coming from right outside of the integral, right? So s squared, and now we just get to evaluate this last piece right here. And actually, we already said that that was just f of s by definition at the beginning of the problem, right? Here it is right here. Okay, and so that's the second derivative. Now we can just kind of clean it up a little bit, right? So this is the second derivative of an arbitrary function. And what does this equal? Well, negative f prime of 0 minus s f of 0. And then we get to add an s squared f of s like so. And so that'll be our final transform. Okay, so that's it. The reason I wanted to make this video was because for the rest of ordinary differential equations, you kind of just take these results for granted. You'll probably never actually solve for them in the scope of a differential equation because you will have been expected to solve for them before, and solving for them over and over and over again is just redundant. So as you can see, we turned an equation of a second derivative, right, into something that looks a lot more like an algebraic equation. And that's kind of the point of the Laplace transform. That's why it's so useful for ordinary differential equations. It's because it ends up turning a long ODE into a long algebraic equation. And sometimes those algebraic equations are much, much easier to solve for than a long differential equation. Okay, but thank you everybody for watching. In the next video, I think we'll get into taking Laplace transforms of some actual functions that we know. Okay, I'll see you later.